So common resources are rivalry in consumption, but they're not excludable. Now, they're typically not excludable for one of three reasons. One, there's no existing rules to govern the use of the resource. It could be due to jurisdictions or most international, like international water, international properties, don't have any rules to govern its use. Second, even if there are rules, maybe the exclusion cost it's very costly. So I'm sorry, the enforcement of these rules are very costly. So the ocean is very large. It is very difficult to patrol the forest, to patrol the ocean all the time. And finally, this is probably the most common of the three. No clear defined property rights, right? Who does the ocean belong to? And if the ocean doesn't belong to anybody, then there's nobody with an authority to enforce when the waste is being dumped. Right? Okay. So here's a video. I suggest to check it out to give you a nice presentation on the fishery problem. Okay. All right. Tragedy of the comment. Okay. So it's the open access, the open access property of common resources that will lead to overuse. So solutions, we'll talk about three different types of solutions: government regulation, cooperation, and privatization. Okay. So before we begin, we have to understand some physical characteristic about fishery. And fishery is a great example because many renewable resources exhibit the similar type of property. Also, a fishery, because fishery is so common across all cultures, that every policy that you can think of for managing this common resource, right, has been applied to fishery to some degree. Right? So understanding the fishery problem will give us a lot of room to work with, a lot of examples to think about. Okay? All right. So with any renewable resource, right, we have these we'll break it down into three parts. First part here, constant return. What is constant return here? We have input. So we're going to simplify the model here. With the input is only number of boats. So as we put in more boats, we get more catch. From 1 to 4 here, we can see that the line is straight. This is called constant return. For every boat that we put in, the total catch is increasing by a fixed amount. Okay. In another word, we can say the marginal catch is positive and constant. Okay. Now, once you get past this red line, then you have diminishing return. So as you put in more boats, total catch is still increasing. However, it's increasing at a decreasing rate. Okay, we can also say the marginal catch is positive, but it's decreasing. So it's becoming less efficient. You're still getting more fish as you put in more boats, but the amount of return is decreasing. And finally, you get to the last part here where it's absolutely diminishing return. That means as you're putting more boats, your total catch actually goes down. Right. So marginal catch is now negative. Okay. All right. Now, because of this property of fishery and many renewable resources, you can see that right away there must be an optimal amount, right? Because anything beyond this obviously is inefficient. You're putting in more resources, you're putting in more effort, you're actually getting less in return. So the optimal must be somewhere here, right? Either be in constant return or diminishing return. All right. To set up our fishery example, let's make some assumptions first. Okay, so we're gonna make the math very simple. So these assumptions are gonna help us make the math very simple. First, marginal cost is constant at $260 per boat. Now, this marginal cost includes environmental costs, includes the fuel, the crew, labor fee, and etc. etc. Okay, so imagine this is how much it costs to operate a boat, right? Now, second, the market value of the fish is $1 a pound. Okay, this is gonna make our math very simple. Right. Let me go back to number 1 first. Marginal cost is constant. Now, in chapter 3, remember that we typically assume that marginal cost is increasing as more boat comes in. That is more realistic. That is a more realistic assumption. However, it doesn't really add much. It doesn't really add any information or useful insight. If we make that assumption, it just makes the math more difficult. So we're going to go with a constant marginal cost here. And finally, third assumption is that each individual is only interested in maximizing their own profit. Okay. All right. Now, again, before we dive in, we need to do a refresher on some of these definitions. Now, most of these should look pretty familiar for those of you who have taken micro econ, and if not, that's okay. They're pretty straightforward. So first, total revenue. The total revenue, also known as sales, right, is just by definition price times quantity. And for us, it would be very simple. It would be $1 times the total of fish caught in pounds. Okay. Marginal revenue. Now, that is the amount of revenue generated by the last boat that enters the fishery. Okay. So, in another word, right, by adding this next boat, how much did the total revenue increase? And to find that is very simple. You just take the new revenue, right? What's the new revenue now minus the old revenue? So you find the difference. Okay. Total cost. Total cost is just the total cost of the for the fishery as a whole. The only input we have right now is boats, and the average cost is the same for every boat. It's $260. So the calculation is very simple. You just take $260 times the total number of boats. Okay. Marginal cost, right? Marginal cost is the cost of the last boat that enters the fishery. Again, like I said, realistically speaking, this should be increasing as more and more boats enter the water. However, for this model, we're going to assume that the marginal cost is constant at $260. And so, but if you had to figure that out, you would simply take the difference between the total cost. The main thing we'll want to pay attention to is total profit. Okay, and total profit simply is total revenue minus total cost. Okay, and this is, again, when we say total, we mean the total profit for the fishery as a whole. Okay, so that's our setup, right? And with that setup and these definitions, then we can fill in this table. And from this table, we're going to be able to see what is the optimal number of boats that should be in the water.